Okay, let's begin. Welcome back. Happy Monday. You can believe Mondays are happy. It helps. We all know the truth. We're beginning hypothesis testing. We've got 5 more lectures. I'm going to spend the 5 lectures trying to address issues in hypothesis testing. I want you to know approximately what a Bayesian does. Being able to execute everything and understand how everything compares is probably too much for 5 days. It would probably take a whole semester to really digest all of the issues, but I'm going to point out what the issues are and let you think about it conceptually, and then we'll work out some examples so that you can do things analytically as well. I don't think we'll have time for the full-blown comparison in the Lindley-Bartlett paradox, which is a description of the gross disagreement between Bayesians and non-Bayesians in hypothesis testing. I want to point out there are cases where we do agree with each other. Our interpretation is just different. Kind of like when we do estimation. The issues are not in one-sided tests like this. In one-sided tests, we have a rough agreement, Bayesians and non-Bayesians, and I'll try to explain why. It's in sharp testing. So sharp tests look like this. So the sharp tests are the two-sided tests, sometimes people call this, or the simple versus composite test. There's lots of ways to do this. So sharp testing, some people call it the two-tailed, two-sided test. I hate this name because it's telling you about the process, not what you're actually doing, exactly what you're testing, but it's describing the process to you. And maybe a Stat 101 student likes that because they know, oh, okay, I use both tail probabilities, not just one of the tail probabilities. So I understand where the name comes from. I still just don't like the name of the test. Two-sided testing, or sometimes people call this simple versus complex or composite. I've heard it said both ways. Or composite testing. So AKA what all that means is something like this. Theta is equal to theta naught versus the alternative is theta is in one of these tail directions. And if you know about computing p-values, the alternative is never used except assigning the tail direction that you run over. So really you just use the null in all of these tests. And so Bayesian tests are a little bit different, where they'll do a direct comparison between the measure on the hypothesis and the measure on the alternative. So they'll place the posterior probability on the hypothesis, conditioning on the data that you have. So the Bayesian will do things the Bayesian always does. They put the probability distribution on the thing that they're trying to understand, which is wildly different from the Fisherian or the Neyman-Pearsonian thing, where they end up computing the probability of your data in more extreme data conditional on the null hypothesis. So the alternative just directs the tail direction. Everything I'm saying is Stat 101 in disguise. So you should have some familiarity with at least what a hypothesis test is. This is a weird test. I'll just kind of point out to you. At a glance, it's weird. It's like, what's the cardinality of that set? So I'm thinking of theta as a scalar right here. It's 1 point. So it's very countable. What's the cardinality of this set? It's infinite, and it's uncountably infinite. So comparing these two sets to each other is a little bit strange. If somebody asked me what I thought, especially in the case like, I'll just say, this might be akin to the one-sided test, but if I do something like this is the big culprit test, where I'm going to compare this one data point against everything else. I already know which one I believe. And so the question we already know, is it close enough to theta naught before we're willing to fail to reject it or reject it. Again, the size of these sets is really contentious, and so it sets up a bad argument. And so all the arguments ensue from tests like this, not tests like that. And the reason why is because there's kind of an automatic calibration in tests like this that, and if you've done this before, the p-value for this test right here, if I switch the null in the alternative direction, if I switch the null to the alternative, then the p-value for this question, if I switched it to this, h naught theta is greater or equal to theta naught, versus theta is less than theta naught. The p-value for this test would be 1 minus the p-value for that test. So what I want to point out is something about additivity. They add up to 1. I'll say for a Bayesian, when they do a test, because everything is a probability on the test, their posterior probabilities of their null, 1 minus that is their posterior probability of their alternative, if we're just comparing two tests. We're just comparing two different hypotheses. So Bayesian tests are always additive. So they're well calibrated and complemented by the alternative. P-value calculations for one-sided tests have that property. And this thing right here doesn't share that property. So if you've ever computed a p-value for a test like this, if somebody said, well, now compute the p-value for this right here and flip the roles, you wouldn't know what to do with that. It wouldn't make any sense to you. You'd be like, how do I condition on this as a null? And 1 minus the p-value for this test has nothing to do with the p-value associated for that test right there. Obviously, you'd be thinking, if somebody asked you what's the probability of this being true, you'd say 1. So it's just removing 1 point from the space. So it doesn't have that additive property. And so I'm going to point out this question doesn't even make sense as phrased. And that's what we're really arguing about. And we're never going to come up with a solution to this because the question is flawed. Okay, so I want to point that out. Saying that, sometimes you might want to say, is theta close to theta naught, and would I reject that as a candidate possibility, which is a different question. And then you're asking how close do you need to be, and you're really asking a relative question. And calibrating that relativeness is something that most statisticians are too cowardly to do. Most scientists are too cowardly to do that. So why? Because it puts the responsibility on the scientist or the statistician and not on the method. So you can't just say, well, I just looked it up in the book. That's what's happening. So people are flawed. People don't like to be consistent. So they don't want to take responsibility. We've seen this all before. So I'm going to teach you what these issues are. And so at least how you address these things, and maybe at some point you might ask me, what would I do in certain situations? And I can tell you. Okay, so I want to read a few statements. I posted these online. So just as a heads up, I posted some homework problems for us. I put on 2 different bundles just to compartmentalize it so it didn't seem so overwhelming. But there's not a huge amount of problems right here. They're all due with the final, so you'll be emailing me all those problems. So not too many. Some chapter 7 problems, just a few more, and then some chapter 8 problems. So give you a little bit more practice. We can do a review session next week. So we'll go through some of this. We can do a review session all through the summer if you'd like, if you're so inclined as well. There's a lot of material in the book. So a lot of things that we're comparing and doing it in one semester is a little bit difficult. There's 2 different statements that I put on here. The BASP statement on p-values and ASA's statement. This is at least a draft of the statement. So I wanted you to see the original draft. You can go find the final report if you want. It's rather depressing from my perspective. I was like, yay, you're finally talking about this again. Boo, you came up with the same nonsensical solutions. The Bayesian recommendation was the one that really made me, I didn't like it. I'll tell you what it is later. So the BASP statement I put here, this kind of sent a shockwave through the statistical community. So you can read through these. I'll just summarize this a little bit. It's 2 pages. But here's the kicker. So Basic and Applied Social Psychology, BASP 2014 editorial emphasized that null hypothesis significant testing procedures. That means the name and Pearson lemma. So everybody uses different language, and when you jump out into other disciplines that play around with this stuff, they'll come up with their own stuff. So I'm just going to replace that by the name and Pearson criteria. So the null hypothesis, what do they call it? Significance testing procedure. And that word significance is contentious as well. And your Stat 101 teacher told you that. So, and they said, we don't really mean it. So we'll go through all of this. So there's definitely some pathology running through the field. So it has a lot to do with history. The Basic and Applied Social Psychology 2014 editorial emphasized that the name and Pearson thinger-binger is invalid. It's actually valid. What Fisher said was invalid. Neyman and Pearson in the typical paradigm, it's mathematically valid, and I'll tell you what it does later. So they're mathematically correct, and what they were actually trying to do was clear up some of Fisher's inconsistencies and his invalidity. Neyman thought that he would be, well, probably Egon Pearson probably thought he would be making amends with Fisher by correcting him. Fisher had a big fallout with his father, Carl Pearson. So I can tell you more about that. Neyman Pearson, baby Pearson, came in and said, hey, let me fix up your stuff for you and you'll appreciate me. It didn't happen that way. So they got into a war. So didn't like each other. Fisher would heckle them all the time. But what Neyman and Pearson did was take one of Fisher's ideas and at least make it statistically valid, mathematically valid. How you apply it, Fisher didn't like it. And I sympathize with Fisher about it. There's just too many inconsistencies in what he proposed. However, to allow authors a grace period, the editorial stopped short of actually banning Neyman Pearson. The purpose of, and you can think of that as P dux alpha. So P dux alpha you reject, and I think you guys have all seen that. So P value small, whoa, reject, so great. You know, how illuminating is that? So they're banning that thing. So P value small, and that's what you report, and that's the conclusion, you're out of their journal. They won't publish that. The purpose of the present editorial is to announce that the grace period is over. From now on, BASP is banning P dux alpha. It's a statistical procedure. With the banning of the null hypothesis significance testing procedure from BASP, what are the implications for authors? Following are anticipated questions and their corresponding answers. Will manuscripts with p-values be rejected automatically? Answer, no. If manuscripts pass the preliminary inspection, they'll be sent out for review, but prior to publications, authors will have to remove all vestiges of the null hypothesis significance testing procedure, i.e. P dux alpha, p-values, t-values, F statements, statements about significance, differences or lack thereof, and so on. So all that stuff. So all that Stat 101 stuff. You touch it, you're out. It's pretty extreme perspective. I would want to know which p-value, how they came up with it, what is its measure, is it coherent? We'll talk about all of that. So there's some p-values that I don't wince at, and some of them that I'm like, you didn't answer any question. So this is just a game. I think they should have differentiated those two things. And they further the confusion, in my opinion. What about other types of differential statistics, such as confidence intervals or Bayesian methods? So answer to question 2. Confidence intervals suffer from an inverse inference problem that is not very different from that suffered by P dux alpha. So usually the typical pivotal p-value thing, and this is what we won't cover, but it's covered in chapter 9. It says here's an interval for values that would not be rejected under P dux alpha, and here's a range of values that would be rejected, that P doesn't duck alpha. And so that's the pivotal thing and one interpretation of a confidence interval. And some people do that, and probably that's the way you learned it in Stat 101. There are exact tests and other types of intervals, so exact coverage intervals and not just the asymptotic pivotal thing. But they're right that the typical confidence interval is very linked to what we're doing in hypothesis testing, and hopefully you've seen that before. And that's sometimes the way people teach a confidence interval. It's not the coverage probability, but rather here's values that you wouldn't have rejected under this test right here if you go through the two-sided thing. So just invoke the procedure. So okay, good. So you can't do something that's exactly the same and get away with it. So they go in and they say a few things about it, they kind of ramble. Bayesian procedures are more interesting. I kind of like that statement. Totally vacuous. So I agree. They're more interesting. But I think a lot of things are interesting. But that's not a reason, because that's a personal thing. So you're interested in it, that makes it good to you. So the usual problem with Bayesian procedures is that they depend on some sort of Laplacian assumption to generate numbers where none exist. The Laplacian assumption is that when in a state of ignorance, the researcher should assign an equal probability to each possibility. I hate this because they're pseudo-Bayesians, and I'm sorry to those guys. So they don't quite have it right. So what they're saying is that Laplace assumed uniform priors on everything. So Laplace did not, so on variance, he used 1 over sigma squared. So he did not use a flat prior. So generating numbers where no numbers exist, they're placing weights on theta, and those values of theta, if we've written them down, exist. So it's a rather abstract way of saying something, but using uniform priors or something like that are not the only thing going. There's a lot of different types of priors that express ignorance. And so I would agree if it's a shift parameter, then of assigning uniform prior probabilities to it probably makes some sense. And we'll see that. So I think you need to explain what you're doing, show how it works, show how it compares to other things. I think that's what a paper should look like. That's not what they want, exactly. So consequently, with respect to Bayesian procedures, we reserve the right to make case-by-case judgments, and thus Bayesian procedures are neither required nor banned. I think that's the way everything should be. So if they were more reasonable, i.e. appealing to me, so that's what we'll define as reasonable today. Are any inferential statistical procedures required? No, they say. So I just want to point out, why is social psychology coming up with this? Why did they do this versus somebody else? Why are they just so sick of this p-value game? Any ideas?
Maybe because people are misusing it.
People are misusing it. Good. That's true. Other people misuse it too. So what's going on, and what is it about social psychology?
I can't replicate experiments.
It's true. So the replication rates are terrible. So under all this stuff, you should have a 5% error rate. So you've kind of built it into the journal that 5% of the conclusions should be wrong if everybody is doing the right thing, i.e. they have the correct models. So the data was generated from their model. So what you're actually rejecting in a hypothesis test is the model itself, and not just the hypothesis, but your model assumptions. So sometimes people might be rejecting their tail assumptions, what they think about the tails. So they think they're Gaussian and they're not. So it could be that. It's really because of what most social psychologists do. I get these emails periodically. Somebody from the University of blah, blah, blah sends me, please spend 20 minutes and do my thesis for me. Here's this questionnaire of 500 questions, answer the heck out of them. Or 15 questions, it won't take you too long. Here's $10 if you do it. I don't do it. So no, I don't even think it's good science to do that. So I think that it's lazy science to just always have a questionnaire and a survey, and that's their whole PhD. And if they send it to enough people and N is really big, they're going to reject. So if N is large, obviously their model is wrong. Obviously their hypotheses are overstated. And so even if they're close to the truth, if N is big, they will reject. And so they have an automatic procedure for rejecting. So I have an automatic procedure for rejecting. Reject, reject, reject. You know, so people don't like that one. You know, but they're doing a whole bunch of smoke and mirrors to get basically the same conclusion, auto reject. And that's significant. So too many surveys in that field. I do think that social psychology might be one of the most interesting fields. The data is messy. The need for really good statistics is paramount in a field like that. Versus like if you were at CERN or something like that, smashing particles together over and over and over again, you can detect these really tiny effect sizes. And so, because you've got replication of the same process over and over and over again, and you can do it a bazillion times and estimate epsilon. And so, I would say groups like that are repeating the same process. Humans are a bit messy. We're not the same process, and it's certainly not IID. So, might be conditionally independent, but our processes are different. So they're non-IID. So even invoking that sort of stuff, you're rejecting probably that assumption. Plus, people lie, you know, on surveys. And if you've ever taken a survey, you know. So it's like, yeah, I kind of feel, but I would rather answer this. You know, they're not complete a lot of times. So it's not that we're lying, it's that the survey isn't asking the right questions for us sometimes. So a lot of times when I'm taking a survey, the answer is, it depends. Okay, you can read through that, but BASP did that. ASA jumped on the board because ASA are leaders. So, and they decided they would readdress this and invoke a few commissions. So, you can read through this, and there's some good commentary in here. I like the statements. Their overall conclusions that they ended up writing papers on. There was a Bayesian camp and a non-Bayesian camp, and they both wrote about their recommendations, and they didn't get anywhere. So the Bayesians, unfortunately, said, well, maybe you should just make the significance level more harsh. So instead of using a p-value of 0.05, why don't we make it 0.01? Same game's gonna happen. You can do this ad nauseum and not get anywhere. So that was disappointing. I did ask Jim Berger about it. Why did you guys do that? You're on the commission. And he said, well, you know how committees are. Yeah. So we had to write something, we couldn't agree on anything, so we came up with this stupid thing, and it's at least a little bit better. So, super, I appreciate his honesty, thank you. So, in February 2014, George Cobb, Professor Emeritus of Mathematics and Statistics at Mount Holyoke College, posed the question to an ASA discussion forum, why do so many colleges in grad schools teach P is equal to 0.05, or not P, but alpha is 0.05. P ducking that. So, but we understand what he means, and certainly George Cobb knows what he's talking about. But let's just be careful, because I would call you out on that. So, because that's still what the scientific community and journal editors use. Question, why do so many people use P is equal to 0.05? Because that's what they're taught in college or grad school, so it's certain. We teach it because it's what we do it because it's what we teach. This concern was brought to the attention of the ASA board. It's like, I kind of read through this, and I'm imagining people 100 years ago going, are they that big of morons? And everybody already knew this. You know, there was no secret here. It sounds good. I want to point out there's been a number of articles. I do like some of these. I would encourage you to pick them out, skim them, read them. I've been in a lot of discussion groups that use these papers. Friends of mine from across campus and scientific disciplines will read these papers. They'll call me up, say, can you join our group? They never really understand what I'm talking about because I can't get it done in 30 minutes. So, but they say, geez, I've been using this p-value thing. There's this paper that was written, it's science's dirty secret, the scientific method of testing hypotheses by statistical analysis stands on a flimsy foundation. So another article, numerous deep flaws in null hypothesis significance testing. So Science News article, 2014. Statistical techniques for testing hypotheses have more flaws than Facebook's privacy policies. Ouch. You know, and that was 2014. And so we see what's happened. So the p-value game, what's the big harm? You know, we understand the big harm now with Facebook, so you can weaponize that. What's the big harm with, it kills people. Don't want to be dramatic. So, a lot of things kill people. But I have heard people go off the handle and say, if you don't pay attention to this, you're killing people. That actually doesn't win arguments. I've tried it. It doesn't. So, people realize you're being hyperbolic. Anyway, it's kind of true. Science News article on blah, blah, blah. Week later, statistician and Simply Statistics blogger Jeff Leake responded, the problem is not that people use p-values poorly, he wrote. It's that the vast majority of data analysis is not performed by people properly trained to perform data analysis. I really love that. So you've got to have the data analysis police there. So this also doesn't appeal to me. It's complicated, you guys shouldn't be doing it, let me do it because you don't know what you're doing. And so I don't believe that either. It must mean that we're conveying poor concepts somehow. Does anybody know who Regina Nuccio is? She's a professor in this department. So she's an ASA fellow. She works up in DC. She does communication forums. She has taught a communication class, but she writes popular articles on statistics, and she can convey things to the masses. A lot of us are just overly technical, and we're not able to do that, and Regina does a really good job. So if you've ever met her, you'll know she lost her hearing a long time ago when she was a kid, and so she has a cochlear implant. It's actually fascinating, just learning all about that as well. So if you ever get an opportunity to talk to her, she's super interesting, and her articles are phenomenal. I don't think she says anything that we don't know already, but she conveys it in a way that is digestible and not in an attacking mode. For a lot of these papers, I think they don't win fans because they're always attacking your intelligence. Probably doesn't work. She posted, wrote an article in Nature entitled Statistical Errors. So that's pretty cool. You can keep reading through this. There's a lot of good anecdotes in this thing, but I think we've at least understood the point. There's problems. And there was a forum recently on p-values and its all their problems. Another forum is down in Carolina this next week. They're putting together a discussion on it. I don't need to go to that. So I already understand what's going to happen. But you guys should check out these forums and at least see the contentiousness involved and try to convince yourself you need to understand what these issues are they're talking about. Because not all tests suffer the same consequences. My experience is even very good statisticians are unwilling to listen to comparative answers. They already know what they want to do. Don't you dare tell me that the last 20 years of my career has been a sham. So we didn't say that. We just said it changed. So I'll try to explain what all this means. So you can read through that. There's a couple articles from the frequentists, the so-called frequentists, I like to call them, and the Bayesians. Okay, so keep in mind, those groups do overlap. Bayesians can be really good frequentists. So Neyman and Pearson is designed to be a frequentist procedure, that if you repeat the procedure over and over again, you'll reject at some rate that's calibrated by alpha. So if you're ducking, when p-value ducks alpha, your type 1 error rate will be alpha, and you'll be minimizing your type 2 error rate. So that's the name of the game for Neyman and Pearson. And I'm going to try to describe what all that looks like, and eventually I'll mix in the Bayesian stuff. So I think you guys know this, at least you're aware of it. It might make you feel a little bit upset. I remember when I was taking a history class in college, and my professor said, yeah, this is the way it is, but if you go and talk to this fool down the hallway, he'll tell you a different story, but he doesn't know what he's talking about. And I was like, oh, that's why I hate all this stuff, because there aren't answers. But there's a lot of answers in statistics, and we suffer from some of the same problems of history as well. So every field does. Okay, so let me just remind you what we're doing. We're basically thinking about two different hypotheses. So this is your truth. And then you're going to make some decision. It can be one of these two things, and all of this can be extended to multiple hypotheses. And if you want to think about how to do that, you can just compare one thing to every other thing and go through. If you had k different hypotheses, you can think about the k choose two different hypotheses. What most people do is they'll compare to one model, and it's equivalent to doing that. It's comparing one model, every model to one baseline model, and they'll baseline everything. You could come up with the same thing by looking at k choose two different comparisons. I'll say a little bit more about that. Obviously, if the truth is h naught and you decide h naught, you're correct. Same thing happens over here. You'd be correct if the truth was the alternative and you rejected the null. This is called so if the truth is h naught, so the null hypothesis, and you reject it, you've made a type 1 error. And these are called type 2 errors. So when the alternative is true and you fail to reject, or you accept your null, and I'll accept that lingo in this class. So this is an error. I will point out, so this is type 2 error. All of this stems from the language of you're not allowed to accept anything is truth. You can only reject truth. It comes from Karl Popper. And it's basic logic. How do I know something's not true if I can't observe it? You don't know. You know, just because you haven't observed it, all you know is it's unlikely in where you've looked. So this is the black swan phenomena. So if somebody says there's no black swans out in the universe, I walk out into the duck pond, I look at all the swans out there, and I count 5 white swans. I don't see any black swans. I go, confirmed. There's no such thing as a black swan. That's obviously, we don't know. So you don't know about things you can't observe, but possibly you can observe things that are contradictory to a hypothesis, and so you know it's not true. And so if I told you, I'm 85 years old, I was raised in the deep south, I am a billionaire, you would have a number of different ways to discount all of those things. So you could look up records, see data points, go, I've got his birth certificate, he's not 85 years old. So he didn't grow up in the deep south, and he's certainly not a billionaire. So you could probably find all of that information, and you could reject that. So Scotland makes stuff up. If I did a really good job, maybe I could be a politician. We'll talk about that later, what I call political priors. So things that no data can change your mind on things. So we'll look at that later. Okay, so I'll just point out what Naiman and Pearson do, or I'll say the likelihood ratio test calibrates things to a fixed type 1 error rate, and it minimizes the type 2 error rate. So that's the whole thing we'll prove, and we'll get around to that eventually. Let's look at some examples first. So I'll do this a little bit out of order. So let's just look at it. So the likelihood ratio test. Ratio test stat. It looks like this. They call it lambda in the book, and they define it to be this creature right here, where I'm going to look over the maximum over theta in my null set. I oftentimes will write it like that, theta element of a null. Sometimes I'll do something like this, and I'll write it out like that right here. This will come in as a ratio. So I just want to write down what my hypothesis is. Theta is an element of some values right here. So I'm imagining some model, f of x given theta. I've collected data from that model, and this is going to be some range of values, and I'll call this the null set. And so when I'm maximizing over this range of values, I'll oftentimes write that max theta belongs to the null set. Sometimes I'll change this notation and I'll just write theta as an element of H naught. And I mean the exact same thing. So if I change my notation, it's just because that's how I'm thinking about it in that particular moment. This is going to be a maximum over all of theta. So this is the global maximum, and what we're going to be maximizing is the exact same functions, but just over different ranges. So that's the likelihood ratio test stat. Sometimes I like to call it the max likelihood ratio test stat because it's using maximums. I just want to point out, this is the basis for Neyman Pearsonian testing. And so this is going to be equal to some number. And this number right here, keep in mind this is a maximum over everything, and this is a maximum over a constrained set right here. So this theta right here is going to comprise H naught union H alpha. So it's the union of both sets. So it's the entire space that you're looking over. This is going to be some number. Since this has more candidate values you can maximize over than that right here, this number is necessarily going to live between 0 and 1. More stuff to maximize over here, so this has a chance to be bigger. Sometimes they're exactly equal to each other. So I'll point out that if it's 1, this is weight on H naught. So the bigger this number is, the more weight I have on the null hypothesis. It's in the numerator. I think that that's better because it's bigger than maybe that. So if it's 1, it's just because they're maximizing at exactly the same point. And so the 0 is weight on the alternative. There's another way to write this, and I'm just going to make this note real quick. They do this later on in the book, and I think this confuses people that they switch everything over and they consider another test. And I'll say this is an equivalent test. And there's a problem in the book that asks you to prove this. I don't need you to do that, I need you to understand it. So another equivalent test to the max likelihood ratio test is to look at this test statistic. I'm going to maximize over theta in the null space. I'll take my likelihood. So the numerator is exactly the same. And then I'm going to divide by the maximum in the alternative space. So the only thing I've changed down here in the denominator, so all of this is in the denominator. All of this is in the numerator. So I've changed things a little bit. The sets that I'm maximizing in the denominator. So this is equivalent to that test right here. But the ranges of values that this can take on are a little bit different. And so I'm going to say this is equal to k, and k can range between 0 and infinity. And that's all this is doing, is it's just changing the range of values. Now this thing could be really small right here, and that could be really large. When I bury both hypotheses into here, I've got some overlap in the numerator and the alternative, and that's what bounds everything by 1. Make sure you understand that these are equivalent tests, because later on in the book, they switch to that. And I end up saying it's equivalent to the likelihood ratio test, and I think people miss that point. So when you go through the proof on Neyman and Pearson, keep in mind the condition you're giving really is equivalent to using the likelihood ratio test statistic. They don't say it explicitly, unfortunately. So, but that is the connection. So very similar sort of thing. So let's look at an example. This example is in your book. And don't think we'll get to my second example. But I'll write it down at least what we'll do next time when we pick up. And we'll pick up a few ideas right here. So here's our example from the book. So I'll just draw out f of x. F of x given theta, it looks like this. Boom. Where this is going to be theta. Right here. Does anybody know what this distribution is? What would you call this? I love it. I would call it exactly that. It's a shifted exponential with rate parameter 1. So the rate parameter is not, usually you'd have it sit like a lambda right here or right there. So that's 1, shifted exponential. I'll just keep pointing out, this is x1 right here, the minimum value, and we've got some big value over here. We can already tell because we've got the parameter sitting on the boundary, the order statistics have something to do with the maximum. That's always true. So that's what the distribution looks like. The likelihood's a little bit different. So the likelihood function is going to be proportional to e to the minus sum of the xi's plus n theta. So all I did is I just plugged in an xi right there and took the product across it. And that's the likelihood function. There are some constraints on here. I go from 1 to n. And so I'll write down the constraint that x1 has to be greater than theta. So theta has to be less than x1 in all of this. Because that's good. When I look at this thing right here, this is an increasing function. Keep in mind that negative sign I dragged inside right there. So that's why it's a plus. Nothing's inside of that negative sign isn't inside of the parentheses. So this is an increasing function of theta. We can see what the minimal sufficient statistic is. It's sitting right here because that's the only place that involves both the parameter and the data itself. I can factorize this out from that. So this doesn't tell us anything. If I did have a lambda sitting out in front, right here, a rate parameter, this part would be sufficient for figuring out the lambda. This part is sufficient for figuring out where the shift is. So just things you can think about. We make the problem a little bit more complicated. So this likelihood function looks like this. It's an increasing function. And it's bounded. So theta has to be less than x1. So that's good. So this is a function over theta.
Let's say x1 without an x.
Yeah, this says x1 right here.
Okay.
Let me draw it again.
The chair would be like, yeah.
Let me make it bigger. The likelihood function looks like this. x1, that's theta right there. So now we can just kind of perform this test. So what I might do, I might compute this. Oh, and let me just fill in one thing in 2 seconds that they give you a theorem in the book. They say you only need, this only depends on the data through the sufficient statistic. And that's because you're using it. That's true for all likelihoods. So they invoke the factorization theorem to prove that. They say this is hx, they call this g of theta given t of x. So they do that factorization. They do the same thing down here, h of x, g theta given t of x. We'll do this in the next example. The h's cancel, and everything just depends on the sufficient statistic through factorization theorem. That obvious statement is in the book, so you can read through that. So, and the proof is that. Okay. I love likelihoods because they just automatically get this right. I can just use sufficient statistics, don't need to worry about anything else. keeps me in bounds. So this will look like the maximum over theta, let me make sure I got my direction right, less than or equal to theta naught. The maximum over all of theta, and here's my likelihood function, e to the minus sum of the xi's plus n theta. This is e to the minus sum of the xi's plus n theta. You can already see that the e to the minus sum of the xi's cancels. It doesn't have any information for us. We need to think about a couple different cases. So let's think about if theta naught is here. So if theta naught is there, it's going to maximize at that theta naught value. So if theta naught is less than or equal to x1, what I'm going to write in is this is going to maximize when I plug theta naught into that. Over the entire range, I get to maximize over the valid region of the likelihood. So I would maximize to right there. So this is going to be e to the minus sum of the xi's plus n theta naught divided by e to the minus sum of the xi's plus n x1. So that's for this case right here. This would maximize up to that point. That's the biggest point in the null set. So this is where the null lives, right here. So I'd maximize just in that region. Otherwise, if theta naught is greater than x1, I don't care where you put the equal sign in this. It works out exactly the same. So if theta naught is greater than x1 right here, then the max likelihood in the null range is still truncated at that point because the likelihood over here is really just 0. And so this would be 1. The numerator and the denominator are exactly the same. They both maximize at this point x1. And so let's just look at this function. And I'll make a few points about this. So I'm just going to fiddle around with this for a moment. And I'm going to look at this one. This is the interesting part of the equation. So if you saw this right here, you probably wouldn't be inclined to reject. If you saw this right here, theta naught was less than x1, if this was extremely small, you would be inclined to reject. We're going to have to be more rigorous in what is small and what do we mean by that. We'll calibrate that by the type 1 error rate later on. So we'll put a probability on something. But this right here is just e to the n theta naught minus x1. So I've just simplified the equation a little bit. So this divided by that. And this is for theta naught less than x1. So we can start getting a handle on how small this needs to be before we reject. What we said before is we're going to reject if it's less than some critical threshold. We'll need to figure out what that is, and what Damon and Pearson do is they use this to calibrate the type 1 error rate, that number right there. And so I can change all of this, and I can say this is, take the log of both sides, log of c. This is going to be n theta naught minus x1 right here. I'll just do some divisions real quick. So I'm going to divide by n. I'm going to bring over my theta naught. And then I'm going to flip the direction on everything. Negative plus. So I just unwound this. So if x1 is bigger than this number, and every time I see this right here, minus log of c, get a little bit panicked, but c is between 0 and 1 the way we've set it up, so this is a negative number. So minus log of c is negative. I've calibrated it. I just want to point out this is a constant. This is some number. How big can this number go? This can be anything between 0 and infinity. So there's some condition on how big this can be before I'm willing to reject. I want to point out, this is the rejection region. So this defines a region for rejecting H naught. So if this condition is true, keep in mind, you're given theta naught in the problem, that's your boundary of your hypothesis. This is some number, you're able to pick your seed to decide how much weight you're going to use to reject the null hypothesis. And this is a region of your data. So this is where your data would live, right here. And it expresses a region for your data, for rejecting. Here's the next step that most people look at. And we'll conclude with this. So people will look at this function, the probability that X is an element of the rejection region. Usually this depends on values of theta that I have to think about. For different values of theta in the hypothesis set, this value might change, and we'll see that in the next example. So what's the rejection region for X? It only depended on the sufficient statistic, X1, and so data sets such that X1 is bigger than this, we would reject. I can figure out the probability distribution of X1. That's what I need to do when I'm calculating this probability. So for our problem, it would be the probability that that thing is true, and we could compute it. This is called a power function. It's called B theta, and it's called the power function. So the power function represents the probability of living in the rejection region. And we can say a few things about it. If theta belongs to the null set in here, then we want that probability to be small. We don't want to reject if theta is in the null set, because that's what's true. If theta is in the alternative set, we want to reject. So we want this to be small when theta is in the null set, and we want this to be large when theta is in the alternative set. So those are the two goals, and it's a balancing act. And so we'll have to make trade-offs to do that. We'll come back next time and draw some of these power functions, get a grasp on what they are before we prove a whole bunch of stuff. So that's it for now, you guys. If you want to skim ahead and look at that proof from David and Pearson, we'll probably have it completed by Friday. So it might be a good time to just eyeball it and see what it says. Make sure you understand it. Okay, thanks.